Hello everyone, my name is Sharareh Shirzad and I'm a graduate student at Louisiana State University. This project is related to enhancing the durability and the service life of asphalt pavement through the application of an innovative UV light activated self-healing polymer. In part 1, I will review the production process and characterization of the UV light activated self-healing polymer. Let's start with the problem statement. The use of recycled asphalt materials such as RAS and RAP as a partial replacement for the virgin materials was introduced to reduce the use of virgin material and the negative environmental effects of asphalt pavement reconstruction. However, the main challenge with this alternative is that the asphalt binder in the recycled materials has been subjected to severe oxidation during service life. Application of the hardened and brittle asphalt binder in the construction of new pavement leads to an increase in the cracking susceptibility of the pavement and consequently affect the performance of asphalt mixture adversely. Polymer modifiers have been used to enhance pavement performance and prolong its service life. Polymer modified binders have been often used to increase resistance to rotting, thermal cracking, fatigue, and to decrease stripping and temperature susceptibility. The use of polymers can also lead to greater elastic recovery, higher softening point, enhanced cohesive strength, and ductility. On the other hand, the concept of self-healing was introduced as a solution to cracking of asphalt mixture. Self-healing properties of asphalt may be defined as the ability to recover the original properties of asphalt mixture by closing crack and stopping the crack propagation. However, self-healing properties of asphalt binder are highly dependent on crack width, rest period, and temperature. Using two concepts of polymer modification and self-healing abilities of asphalt binder, an innovative self-healing polymer was used in asphalt pavement to enhance its performance while increasing its service life. The self-healing polymer used in this study is called oxytocin-substituted chitosan polyurethane and was introduced by Gush. The UV light activated self-healing polymer is constructed using three main materials. The first material is called chitosan, which is an important derivative of chitin. Chitin is a natural polysaccharide and is one of the most significant biopolymers in today's world. It is also considered the second most abundant polymer. Chitin is mostly exploited by the exoskeleton of insects, shrimp, and crabs. Chitosan is biodegradable, biocompatible, and non-toxic. Chitosan was selected for the self-healing polymer to provide UV light sensitivity. The second material is oxyton, which is a cyclid oxide compound and was opted to deliver a four-member ring. Cleavage of the four-member ring oxyton results in the production of free radicals. The third material is polyurethane, which is produced through an isocyanate polyol cross-linking reaction. The importance of polyurethane is to provide mechanical integrity and to facilitate the cleavage of the oxytone ring. These three components were selected based on their functionality. The production process of the self-healing polymer consists of two phases. In the first phase, the oxytocin-substituted chitosan is produced by reacting the OH group of chitosan with chloromethyl oxytone. In the second phase, we have to produce the self-healing polyurethane. Polyurethanes are generally made by the exothermic reactions between alcohols with two or more reactive hydroxyl groups and isocyanates that have more than one reactive isocyanate groups. In this study, the light-activated self-healing polyurethane was generated by reacting trifunctional hexamethylene diisocyanate with polyethylene glycol and dispersed oxytocin-substituted chitosan. The produced self-healing polymer is a brownish liquid. The material is poured on a substrate and cured at 30 degrees C and 15% relative humidity for 12 hours, and then dried in a vacuum oven for 48 hours. Fourier transforms infrared spectroscopy, or FTIR, was used to evaluate the synthesis of self-healing polymer by comparing the obtained spectra of chitosan with the oxygen-substituted chitosan, as well as the spectra of HDI with the final product. During the first step of self-healing polymer preparation, chloromethyl oxyton was reacted with chitosan in order to attach the oxyton ring to the OH group of chitosan. The FTIR spectra of chitosan and oxygen-substituted chitosan confirmed the mentioned reaction. The new peak observed at 1348, but only on the FTIR spectra of oxyton, corresponds to CCH3 of oxyton, thereby confirming the successful reaction of oxyton and chitosan. In the second phase, amidogen of chitosan reacts with an isocyanate group of HDI, thus producing a carbamide of self-healing polymer. Due to this reaction, the band at 2260, which corresponds to isocyanate group of HDI, was removed in the FTIR spectra of the final product. The band at 6060 was added, showing the presence of carbamide. This slide presents the thermogravimetric analysis of the final material. TGA results presents the change both in weight and derivation weight with the decrease in the temperature. As shown in these figures, the weight loss was less than 10% at around 163 degrees C. This initial weight loss can be related to evaporation of residual methanol used for washing and isolation of oxygen-substituted chitosan. Based on this result, it can be concluded that the produced self-healing polymer are suitable for use during the asphalt mixture processing. Furthermore, a 50% weight loss was observed at around 350 degrees C. The significant weight loss at high temperature is attributable to the disintegration and degradation of self-healing polymer due to exposure to high temperature. In addition, the derivation weight shows that the highest weight variation occurs at a temperature of around 460 degrees C, which can be identified as a point where self-healing polymer degradation starts. How does the self-healing polymer work? During the appearance of microcracks in asphalt pavement containing light-activated self-healing polymer, different chemical bonds in the polymer will be broken. Consequently, a breakage of the bonds generates unstable free radicals. These radicals will recombine through UV light exposure. During the recombination, the radicals will repair damaged area of the asphalt pavement. Thank you for watching this video. For more information, you can visit Tran-SET.lsu.edu.